then that grade changes for that. So that grade, if you saw it, it'd make you freak out. It probably won't. You guys are seniors, you know they don't matter. For the most part, but just a heads up, just don't worry about it too much. The dean asked me to put them in. Homeworks are looking good so far. Yeah, let's keep on trudging. We're done with vibrations for now. Let me mute myself so I don't echo. I'd like to start a new topic, and this is where we're going to kind of focus our energy for the rest of the semester. I need to start building molecules. And we have to start from ground one, just like we started with vibrations. We have to start with the simplest case, understand that simplest case, and then figure out how to take that simple case and put them together, a bunch of different simple models together, put them together to make something more complex. We saw that logic that we used for polyatomic vibrations last class, where we treated everything like diatomics, and then we made it kind of funky looking, where everything simplified to diatomics. We're going to continue that approach with molecules. Molecules for us will be sums of atoms. We're going to understand atoms, then we're going to add them together to make molecules. Really, really simple idea. But we have to understand how an atom works first. So that's nice because the periodic table tells us exactly where we can start atoms. Just a hydrogen atom. But we can just appeal to Mendeleev. Mendeleev says just go start with hydrogen, and we'll find that that's a very useful way to look at problems. Okay. So a little bit about how we think about hydrogen and most of the time we just think about H2. We know that it's got one proton and one electron. It's the first atom in the periodic table. You guys know that it's got these electronic orbitals, S's and P's and B's and F's. So we know kind of what we expect. All right, and so what I want to think about is, how do I take a proton and an electron, put them together, and somehow get these magical orbitals out? Or even more amazing, and let's give you a hint that if we understand hydrogen, we can understand the other atoms, because all the other atoms also have the orbital, right? Helium also has one S and two S and B. All the atoms have the same, in some sense, the same electronic structure. Where those orbitals lie in energy may differ. Some have electrons in them, some don't, right? Hydrogen doesn't have any electrons in its p orbitals because it only got one. So we get a sense that if we understand hydrogen orbitals, we can understand the other one well. They have very similar structures. So that'll be our goal, right? Understand hydrogen, which is something that we can do very easily, but we can do it. Something that we can write down equations for and solve exactly. We can understand hydrogen atom perfectly, a high precision. And then we'll have to use that model for hydrogen to expand it to larger atoms. Okay? And then we'll put those larger atoms in molecules. Right? That's going to be our goal for the rest of the semester. So let's, just like we've always done, the way we start with this problem is we identify the physics problem associated with the particles we're interested in. With a bond, we thought about vibrations. And so we should think about what that motion looks like for hydrogen. And hydrogen only has two parts. It has a proton and an electron. So let's just kind of think about those components and how they interact with each other. And that will give us some hint on how to approach this problem. Okay, of course, the main part of the atom, maybe the least, it depends on who you ask if it's the most important or least important part of the atom. Maybe that's the wrong way to talk about it, that the nucleus and the electrons are equally important. Well, what can we say about a nucleus? It's heavy, it's massive, which are kind of the same two concepts. And most importantly, it's positively charged. And of course, in hydrogen, the nucleus is just a proton. Right? It's a single particle a positive charge. Unlike an electron, it actually has a shape, has a radius. Proton is an actual, I call it a physical object, electron object, but it's a ball of positive charge that has a size and a shape and a mass. And we can write the mass of that proton down. It's going to be useful to think about the mass of the proton. This is 1.6726 times 10 to the minus 27 kilograms, which is a small number, but again, everything in kilograms for an atom is small. So it might be better to write this in a different unit. But you can basically show that basically 99.9% of the hydrogen mass is just a proton. The proton basically makes all the mass. Right. So that's one component, right? You've got that nucleus sitting in the middle. And what does Rutherford tell us? Rutherford tells us that atoms are these big balls of nothing. There's tons of empty space in an atom. You've got this little nucleus in the middle. Somewhere outside you have electrons, and then nothing in between them. So we got a whole lot of nothing space, and then suddenly we get electrons. Of course, electrons are light. They're point-like. Right? They have no shape, right? And they have negative charge. And again, not particularly frightening concepts, nothing new. But just as a note, we write electrons as E minus and protons as P plus. So anytime you see that, that's what I mean. And then the mass of the electron is 9.1094 times 10 to the minus 31 kilograms. This is a mass, of course, you've seen before. And we talked about this at the Born-Oppenheimer approximation, but this leads to a ratio of the mass of the electron over the mass of the proton, right, of about 1,000. It's a little more than 1,000. So that electron is tiny compared to the proton. So you've got this little tiny object swinging around the proton. Relative to the electron, the proton doesn't really move. We'll formalize that concept that we just take the proton as like a center of an object and the electron is just orbiting. We're going to have to show that that's a reasonable assumption. And we will. Okay, so let's set up our problem. We've got two particles that are in some sense orbiting each other. Actually, I have no idea if they're orbiting each other or not, but we know positive and negative. We have some sense that there's some force between them, right? Some interaction, some electrostatic interaction. So let's just kind of define a coordinate system for our atoms, our atom. And this will be something that we'll use frequently in this class, where I'll define the z-axis to be the vertical axis and x to be the perpendicular, the parallel, like the other one, and then y in and out of the board. Right? I'll try to keep this axis system consistent throughout class. And it's important for us to define a good axis system because hydrogen is a three-dimensional object. This is the first time in this class where we have motion in 3 dimensions. We've only so far looked at one-dimensional motion. On the homework, you looked at a 3D box. But here we really have to be 100% 3D. There is no 1D hydrogen atom. So we have to be in 3 dimensions. That's going to require some more variables and more, we have more coordinates, and the math is going to be slightly more complicated. But if you guys took Calc 3, I think most people are taking Calc 3 at this point. Know that it's not too hard, depending on what professor you get. They go from 1 dimension to 3 dimensions, and I'll go through those calculus fundamentals with you in this class to make sure we're all on the same page. So let's in this coordinate system, let's embed our particles. What we're going to do is we're going to treat the proton as the origin. All right, so we're going to stick the origin of this coordinate system right down in the middle of the proton. And somewhere in 3-dimensional space, we're going to put the electron. I'll put it right here. All right. Remember, it's a point, like we're treating it like a point. Okay, it doesn't really have any shape, but we can, in some sense, pick the position that the electron is at. And what I'm going to draw is a vector connecting that proton to the electron that we'll call R. Oops, sorry. Okay. And so that's our coordinate system right now. All right, we've got R, it's pointing in some position in X, Y, Z. And it's pointing at that electron. The electron is potentially moving. Okay, the question, of course, is how is it moving? Okay. So if this were a classical system, two particles interacting with each other, they're orbiting or something like that, there's going to be a force, right? Could be the gravitational force for if these were planets. Of course, that's not what positive and negative charges feel. They don't feel gravity, they feel the electrostatic force. So we have some force that's acting between them. And of course, if we have a force, that means we have a potential energy. So we can write the potential of this system. Some sense the energy sources of this. And the most important one is the electrostatic potential. And the electrostatic potential is a function of the distance between the two objects, R. And it's equal to some new constants that I'm going to have to write down. There's some new numbers that we're going to have to remember here. Minus E squared. Actually, let's write it like this. Let me write it a little differently. Z plus Z minus. I'll write what those are in just a second. They're just numbers. Over 4 pi epsilon naught. That's a new constant that I'm going to have to write down. Times R. So it has a 1 over R potential. Minus 1 over R. It's minus. It means it's attractive, as it should be. Or at least we think it should be. Actually, let's write a positive value here for a second. Sorry. Let's write it like this, because we don't know if it's attractive or repulsive. Right. This potential is, in fact, if you put a negative sign here, you have like a negative 1 over R. That's basically the same potential as gravity. Right? Gravity and electrostatics have the same 1 over R behavior. We can kind of think about gravity in the same way. But of course, it's electrostatic. It's about a positive and a negative charge. And so what these Z's are, so let's define some parameters in here. These will be useful. So Z plus is the charge of the proton or of the positive particle. And Z minus is the charge of the negative particle. Okay. And epsilon naught is a new number. It's a new constant. And it's 8.854 times 10 to the minus 12. And let me give you better units than the ones I have written here. What units do I like here? There's a bunch of different ways to write the units for this. I like, all right, we'll just do this one. Coulomb square. No, that's a terrible unit. That's so annoying. All right, we're just going to write it. It's called farads per meter. Right, farads is an electrostatic unit. And I'll talk about what this number is. Okay, so this is a constant. I'm just going to write what this is called up here. It's what's called the vacuum permittivity. And in some sense, what it is how easy it is to transmit charge in free space. So the idea is that you think about it like this: if you put a positive particle in water and you put a negative charge in water, like a proton electron, and you ask the question, how much resistance how much conductivity the water has, right? How easy is it for it to transmit that charge from the negative to the positive? Well, in water, it's very easy to do that, right? Water is fairly polarizable. It's easy to move electrons, electrical energy through water or some conductive material. And so water has a permittivity as well. That tells you in some sense the resistance of the material that it's embedded in, the space that the charges are in, transmit that energy, that electrical energy from one point to another. And so this is the permittivity effect of vacuum. It tells you how hard it is to take some charge in the electron and transmit that interaction or that energy to the proton. So it just gives you a sense of some sense of how insulating the vacuum is. Okay, so there, in some sense, that there's some resistance to transmitting charge in the vacuum. There's some resistance. It's a little different than electrical resistance, but it's certainly the electrical resistance of an electron to a proton is a function of the distance is a function of the permittivity. So the higher the permittivity is, the easier it is to move that charge between 2 points. Okay, so it's just a number that tells me something about the fluid, the material that my proton and the electron are combined in, and that's of course just the vacuum. Okay, so what is Z plus and Z minus? Well, the proton and the electron have the same charge, but they're opposite each other. So for this system, we say that the electron, its charge is minus a number E. Right? And the proton has a charge of positive E. Okay, so I can write this as minus E squared over 4 pi epsilon naught R. Okay. And E, epsilon, E is not E like 2.718, not the exponential, but this is what we call the charge of the electron. Right? It's how much charge does one electron bring to the table. And that's also a constant. And we'll just put it right here below the mass. So this is the amount of charge that an electron brings to the table, and it's 1.602 roughly times 10 to the minus 19 coulombs. Okay, if I multiplied this by moles, I would get the amount of charge that a mole of electrons brings to the table. And that's what's called the Faraday constant, which you use in electrochemistry. Okay, how much charge? Right? So it tells you something about the current. Right? Current is how much charge is distributed from one point to another per second. Charge transfer per second. So this tells you how much charge the electron brings. Okay, so it's a fixed number. So the important thing here is that the potential just looks like 1 over R. Okay, there's some numbers, but it's a fixed number. All right, so the potential of this interaction looks like minus 1 over R. It looks like minus. So it's an attractive potential, as it should be. Positives and negatives attract. Okay, so that means that the electron at any distance R feels an attractive force pointed towards the proton. This should give you pause for a second. Because what this is saying is that the electron, regardless of its position, always feels a force pulling it towards the proton. Okay, always. And that force gets stronger and stronger and stronger the closer the electron is to the proton. It's 1 over R. So as R gets smaller, this force gets stronger. So classically, we look at this right here and we say we have a proton vacuum of electrons. The only thing that should happen classically here is that electron should just spiral inwards into the proton until they get consumed. Right? There's no repelling force. As far as I can tell, the proton electron will just go like this. In fact, you can do the calculation. And it turns out that if you assume that this is true, that the electron is just going to get sucked in through Newton's law, into the proton, that the hydrogen's lifetime should be about 10 picoseconds, right? At basically in ground state. So if it's the lowest possible energy combination of the proton and the electron, hydrogen atom should last about 13 picoseconds before the electron spirals in and collapses in on itself. That obviously doesn't happen because we exist. There's chemistry, there's hydrogen atoms, there's molecules. This electron does not get sucked into the proton. So this is already an important consequence of quantum mechanics. Classical mechanics, Coulomb's laws, right, the things you learned in physics too, necessitates that the result of this is that the electron gets sucked in basically instantaneously. But it doesn't. It stays. It's a stable orbit. Right? The electron just stays around the proton and never gets sucked in. So what gives? Right? So where does that happen? Why does that happen? Why is it that classical physics fails so utterly miserably to predict atoms? Like it's not even close. Classical physics predicts that no atom should exist. No stable orbit of a negative charge and a positive charge. Okay, so we're gonna just keep that in the back of your mind that we're already just in the simple world of an atom. We're already in a place that doesn't have a correspondence to real life. Sorry, it is very much real life. The macroscopic world, our visible world. Okay. So we gotta need to resolve that. Why is it that the proton is not just an electron vacuum? Okay, so one of our forces is the electrostatic potential. But we can imagine that this electron is orbiting. Right? You have some sense that this electron is moving around the atom. Okay? So one of the forces is the electrostatic force, but there's an additional force that arises from the angular motion of the electron, right? Orbiting the proton. Right? So we first have the electrostatic potential. Right? And we're going to define a different force, which most physicists would cringe a little bit at me defining this because they call it an imaginary force, but it's a useful way to represent the physics. Is the centrifugal force. Arising from angular momentum of electron orbit. Right? The centrifugal force, right? We've got something spinning. Right? And we know that when you think about standing, whether like you're standing on a what do you call this things that you turn around the merry-go-rounds really, really fast, and you have to feel that force pushing you against the side out, pushing you out. Right? So as this electron is rotating at some distance, there's this additional force being applied, centrifugal force pushing the electron away from the proton. So let's focus on that today. I think that's a more interesting force. The electrostatic force is cool, but it's attractive and it doesn't really solve our problem. It's certainly important, but we have this other force, and the centrifugal force is going to be in the opposite direction. Right? The Coulomb force brings the electron in, but if the electron is orbiting, the centrifugal force is out. Okay, so this should be some compensating force that keeps the electron away from the nucleus. At least we hope. Okay, so let's go again and let's think about angular momentum from the point of view of our electron. So let's go back and define our coordinate system one more time. There's my electron. Right. I have a distance here. I have my displacement vector r, right? And we're going to say that the electron has some momentum in some direction. Okay, it's moving in some linear way. You can kind of think of it like the proton and the electron are at fixed distance, fixing the distance, and there's this electrostatic chain attaching the proton and the electron, and that proton is causing the the electron to swing around like a sling. Okay, so we have some momentum, say, in this direction. And we can define what's called the angular momentum. Which we call L. It's also a vector. And it's equal to the R vector cross the P vector. Okay. So we have an electron that's like this, and it's moving in this direction linearly at some point. We say that the angular, we use the right hand rule. Yeah, this way. And that the angular momentum is pointing out of the board. Okay, so we have an angular momentum vector that's perpendicular to R and P, sticking out of the board. And what does that lead to? Well, that means that the system, the electron now, actually it's pointing into the board. I'm sorry, I have that wrong. Let me actually fix it. So there's an easy way to fix this. I'm just going to make it go the opposite direction instead. There we go. Okay, and so the angular momentum now is out of the board. And what that means is that it's going to swing this proton in the direction of the angular momentum. Right, so it's going to pull this electron. Right, so this electron with this angular momentum is going to spin clockwise around the z-axis. Right, so as we watch that electron, this momentum in this direction, it's going to swing in this direction clockwise. It'll work. Okay. So this is at fixed R. Applying some momentum, P, in a direction, leads to an orbit with tangent momentum, which is angular momentum, L. It's spinning around that axis at some frequency. Right, and we'll have to think a little bit about the physics of this. But let's just kind of think now, right? We have this angular momentum, right? And it's going to, right? It's in some sense, it's applying, it's keeping the electron spinning, and it's applying some of its kinetic energy to this rotation instead of the sucking motion of some of the angular momentum has been, sorry, some of the kinetic energy has been in some sense taken away from the sucking motion of the proton, the electron, the radial motion, and being applied to the orbit. Right? So we have some balance of these two forces, the orbital motion, force, the momentum, the force arising from the momentum of the orbit, and the force of the electrostatic attraction bringing it together. And those are in opposite directions. Right? What we should get in this system is that the force due to centrifugal motion is pointing away. Right? This is what we learned a long, long time ago in Physics 1. So this is kind of where Niels Bohr was in the early 1900s when they realized that the electron has these orbitals, these energy levels, which made no sense. It didn't even make any sense that hydrogen should exist from the point of view as we described. to just suck that electron in. So empirically, the quantum mechanicists of the 20th century understood that there must be some balance of these two forces, centrifugal and the electrostatic, and that it must lead to some stable orbit because that's what we see in the hydrogen. That there are stable electronic orbits. So we know that there must be some solution. This is a really bad, kind of a lame way to do your math, but that's the way quantum mechanics works. Is we have observations and we don't understand what they work like, so we have to come up with something. And we have to use Occam's razor, which is the simplest explanation that explains all of the observations. And so what Bohr and all of them say is that there must be this combination, there must be some certain radii, certain distances, certain orbital lengths, if you will, distances that are stable. There's the one n equals 1, right? The 1s one, there's a 2, there's 3. You have these sequence of stable orbits. And so there must be, right? So Bohr's model, we call this Bohr's model. Which is that electrons have stable orbits where the magnitude of the angular kinetic energy right, which is of course all kinetic, is equal to the value of the electrostatic potential energy. Another way to write this in terms of forces is that the centrifugal force is equal to the electrostatic force, right? But I can also just think of it as you have some kinetic energy arising from this orbit, and that energy has to be balanced in the opposite direction as the electrostatic. So that means the absolute values of those numbers would be the same. There's no difference between the two. And so Bohr does this math, and he comes up with a really, really interesting idea, right, which is kind of the classic. It's wrong, as we'll see, but this idea of the hydrogen atom as being a proton with these embedded orbits around the atom of different radii. I'm trying to make it so that they're nice and concentric. There we go. Like that. And he says that they correspond, they're quantized. Remember, everything quantum mechanics is quantized. So we have the, like what he calls the n equals 1 orbit, the n equals 2 orbit, the n equals 3 orbit. And he calculates that the energy as a function of n is equal to, this is with experimental data, 13.6 electron volts. I'll give you a different number than divided by n squared. All right, he uses experimental data for this, so this is an empirical number. And I'll talk later about where this number comes from. Let me give you that in a different number. Something that you're more used to. We'll talk about EVs in a little bit when we get to hydrogen later. Is equal to minus 1,690 wave numbers divided by n squared. Okay, so he comes up with this value, and it turns out that this fits spectral data perfectly, at least to at 1905. Perfectly in the early 1910s. All right. It does not fit spectral data with modern spectrometers of hydrogen. But at the time, the measurements of hydrogen, which mostly come from the sun, it matches the data that they see perfectly. So that's a great, right? So Bohr just keeps a very simple idea. He says, like we have the, what he says is that that classically we have a balance of two forces, electrostatic and centrifugal. And we know, and he applies this idea of quantization, the idea that there must be these quantized stable orbits where these two things are balanced. And he just goes through the math, that assumption, and comes up with this equation. He has no concept of this number, but he gets it from experiment. So this number comes from experiment, but it fits the data perfectly. Up to the data good in 1910. Okay. There's an important problem with this. And it's that you asked the question, right, about whether this system has this equal, and what this implies is that in all of the orbits, the electron has to have angular momentum. And n equals 1 means you have 1 unit of angular momentum. Here you have 2 units. Here are 3 units, whatever it means to have a unit of angular momentum. But in every state, the proton has a formal angular momentum to it. It is orbiting. So he predicts. So Bohr says that the angular momentum of the electron for each n is not equal to 0. And guess what we find out in an experiment just about 10 years later by Stern and Gerlach, amongst other people, is that the angular momentum of the n equals 0 state is 0. Or sorry, n equals 1. Sorry, there's no n equals 0 state. N equals 1 is 0. So Bohr predicts, right, because you always have to have angular kinetic energy. You always have to have angular momentum, right? Because we always have potential energy, no matter what distance we're at. They're always attractive. So in order to have a stable orbit, you always have to have angular kinetic energy. That means that you always have to have angular momentum for all your orbits. But then you go look at an experiment and you see that the electron at n equals 1 has no angular, none at all. So Bohr was right, but for the wrong reasons, right? Bohr's model only works so well. It's in some sense he got lucky, but it doesn't predict all of the properties of the hydrogen atom, which is frustrating because I almost thought that in some sense, we thought we almost got out of the problem. We have all this crazy shit happening that doesn't make any sense. And Bohr has a really simple idea that empirically fits the data, but it only fits the data that he had in 1910. And then when you get to 1920, it doesn't fit the data anymore. There's exceptions to the rule. So it's an incomplete model. All right, it's just an approximation. So we have to do better. What this means is that this doesn't really work. That this isn't the reason we have stable orbits, it's that there's always this balance. At least we think so. Because we can show that there's a state that has no angular momentum, and that state always has potential energy. But this balance is never achieved. But it exists. So we're not quite there yet. This is an incredible achievement from Bohr. Bohr won the Nobel Prize for this, amongst other things. It's really, really clever that he came up with this model. But it gives us a good start to think about the hydrogen atom, but it's fundamentally incorrect. Okay, so we're going to now have to appeal to a different approach. And the approach we're going to take is the exact same approach we did in our modern quantum mechanical approach. See, back in 1910, Bohr didn't have a Hamiltonian and a Schrodinger equation, and he didn't know to solve for these wave functions. None of this existed in 1910. All Bohr had was some physics and some experimental data, and he just came up with an idea. Right? He didn't have quantum mechanics. We have quantum mechanics in 2026. So what we're going to do is to tackle this problem of centrifugal motion and electrostatic motion, two potential energy sources, separate. We're going to treat them like we do quantum mechanically, like defining some potential energies, getting some operators, defining the Hamiltonian, and solving the Schrodinger equation. So we're going to apply the correct theory, which is once that correct theory was invented in the 1920s by Schrodinger and Heisenberg, they went back and solved all this correctly. Okay, so we can use that. I don't want to go through all the BS that Bohr did because it doesn't work. So let's use the right approach and get the right answer for the right reason. So the question, of course, is the strategy and how we solve this problem. In some sense, we have two different types of motion. We have this radial motion due to the potential energy of the electrostatic. It's a function of R. And then we have this angular momentum, which is at fixed R. Okay, so we can maybe start to think about the hydrogen atom in a kind of a simple way. Is we scan R, we move the electron at different distances, and then for each of those, figure out the angular momentum problem for each of those distances. And then once we understand how the angular momentum scales as a function of distance, then we can solve the radial problem. Right? So we solve the angle part first and then the radial part second. Let me show you how that works. It's a really, really nice way to solve this problem. So what we say is that the hydrogen atom is a separable system. Right? The idea is that we can think about these two forces, these two potentials, separately from each other. One's a function of R, and the other one's a function of angle. All right, let's see if we can get some like geometric sense of how that works. The important factor comes from the fact that the potential has this behavior that looks like 1 over R. Right? It's 1 over R. Right? There are no angles in here. Right? It doesn't tell you anything about which angle you're at. It only depends on the distance. So what we say is that this is a spherically symmetric potential. Imagine that I embed my proton in my coordinate system, right? And I ask the question, what positions in space have some potential energy V? Well, it's all the positions at distance R from the proton. So I can draw my arc somewhere here, but I can also draw it here and get the same answer. Right? I can draw it in any direction. Right? So in fact, this potential energy at a given value is a shell that's radially symmetric. Right? So everything on this surface, if you will, right? Every point on this surface has value V of R. Okay? So the potential doesn't care where the electron is, it only cares about the distance. Right? That's really nice. That's going to be really helpful, that it's spherically symmetric. And it's just like gravity, right? Just gravity works exactly the same way. It doesn't matter which direction two planets are coming together. It only matters how close they are. Just like this. Right? And so what that means is that if we can fix R, then every point has the same potential energy. Just a fixed surface at a given R. And then we have angular momentum, which is at fixed R, but depends on the angles relative to XYZ. Right? Why is that? Well, again, just kind of think of it like this. We have an electron at some distance from the proton. There's my electron in purple. Right? And that electron's position at a given R, at a given R, distance R in orange, depends on the angles it makes with the axis system, right? I can define an coordinate, an angle here, theta, Okay. And then I can project this down into the XY plane. Let me draw this in a different color. And define another angle, sigma. Right? These are just spherical coordinates, right? So the potential, the centrifugal potential, is not a function of r, but it's really a function of theta and phi at fixed r. Okay, so one of the motions, one of the potentials is only dependent on r, and the other one has no dependence on it. It's parameterized by r. The potential energy changes per unit r, but once r is fixed, it only depends on the units. So we have two completely separate physics in some sense, right? This is only dependent on these, and this is only dependent on r. So they're completely separate motions. Now this depends. You can kind of think that they are somewhat interrelated to each other because the angular momentum of the electron may depend on how attracted it is to the proton. Right? But you can see that otherwise the potentials themselves are not specifically dependent on each other. They do relate to each other directly, but they're not dependent on each other. So I can spin this electron around and never change this and vice versa. Okay, so they're separate. All right, well, here's a new problem that we haven't seen before. This is by definition a two-dimensional problem. We never really dealt with a problem that has to be with two variables. We've looked at problems that are one dimension and then made it into multiple variables. Here's a problem, quantum mechanics problem, that implicitly or explicitly depends on two variables independently. Right, so this is a 2D problem, and then eventually it's going to become a 3D problem when we enclose both the terms. Right, so this is what this top problem we consider is what's called a one-dimensional radial potential. Right, it only depends on the length. And this is what we call a two-dimensional angular potential. Right, they just deal with two very different behaviors. Right? And this is going to, as you can see, this is going to require different math than we use. Because now our angles, our potential is not defined by x, y, and z, but angles instead. Okay, so we're going to have to find some way to convert between x, y, and z and angles and r, which you've done in Calc 3 before, I assume, where you've done spherical coordinates or cylindrical coordinates. And you probably don't remember that anymore. That's okay. You probably did it for like 1 week and then forgot about it. But I'll remind you how it all works. Okay, so we have a strategy here. We have some potential energies. We can define some kinetic energies, and then we can define a Hamiltonian and solve for our wave function. And the nice thing is because it's separable, just like our three-dimensional particle in the box in problem step 1, we can solve each problem separately. We can solve, what we'll do is we'll solve the angular problem first, and then we'll go back with that information and solve the radial problem. So we'll solve the hydrogen atom in a bootstrapping line, one by one. We'll figure out how it depends on angle. We'll see that gives us some dependence on R. And then we can use that R, bring it up to D, and solve that problem. So we're going to solve the hydrogen atom in 2 steps. And I'm going to tackle this one first. It's easier and actually the more instructive problem. This up here we'll deal with later. It's not so interesting. Well, it is interesting, but not from a conceptual point of view. So let's start tackling this angular. And we're going to tackle it in a very generic way. In fact, we're going to come up with a theory of angular momentum that can be applied to any kind of angular momentum. And in fact, we're going to come up with a theory right now that I can immediately apply to the rotation of molecules. I'll show you how that works. Okay, for angular. Let's talk about angular momentum. So let's set our problem up. Right, the idea is what we're going to do is we're going to have a proton here. Right, and we're going to basically put a bar between it and the electron. And I'll put the electron right here. Right, and we'll fix it at some distance r. Okay, we're going to fix it r. Okay, and I'm going to just like what we have here is a very similar problem to our diatomic vibration, where I have two masses separated some distance. But in that problem, we stretched it, right? This time, we're going to take that same diatomic effectively. So this diatomic's an electron and a proton. And we're going to spin it. Okay. So to stretch it, we're going to spin. But we can do the exact same approach. We can define a center of mass and think about the center of mass of the system. So where is the center of mass? Well, remember the proton is 1,000, 1,500 times heavier than the electron. So the center of mass effectively is right in the middle of the proton. So unlike a molecule where the center of mass might be between the two atoms, the proton is so much heavier that the center of mass is basically in the proton. Right? This is why we can treat the proton as being stuck in the center of the origin of the coordinate, and we assume it doesn't move because the center of mass is on the proton. So what we're going to look at is the rotation of these two bodies relative to the center of mass, right? And so the electron, if it rotates, is going to have this big radius like this, right? It's got this big giant orbit. And the proton, if I put the center of the proton right here, has this tiny orbit, right? So I don't really care about the proton's motion. Right. So what I'm going to do is I'm going to, since MP is much greater than ME, I'm going to assume the center of mass is in middle of proton. It turns out that actually you can show that this doesn't work, but you have to go, like, your precision needs to be like 1,000 or 10,000 times better than the precision when you take care of this problem. We can relax this and actually come up with a way to measure how the proton wobbles. But we're not going to worry about that at all. It doesn't matter for chemistry. In fact, that's a physics problem more than anything. Okay, so basically what it looks like is you just have a proton and then is like the sun, and that electron is like the Earth and it's just orbiting some radius, so angular momentum. So what I really could do is so I rescale this problem. Is that I've got a proton here. Here's my center of mass. Here's my proton radius. This is my proton here. And then I can just define from the origin an R of my electron, which is just orbiting the proton by itself. Okay. So this is basically just saying the electron is orbiting a fixed body. Right? We'll just assume that that's true, right? And it's a very good approximation to very high precision. Okay, so let's define a few parameters, some things that we can measure about this angular momentum. You can imagine that this thing is orbiting. It has some rate at which it orbits. You can imagine just measuring the time of a lap, some frequency, right? So we can define an angular frequency, how fast it's orbiting. So we can define omega r, which is the angular frequency, right? And it's the amount of time. Actually, sorry, let me replace that. The units of this is how much it takes to span one radian in a second. All right, so it's radians per second. Okay, so it just tells you in 1 second how many radians you go through. Okay. And so what we can say is that this electron has a velocity. Okay. And the velocity of the electron is equal to the angular frequency times the distance. Okay, so this is what we call this is the velocity. Okay, so we've got some electron that's got some angular momentum. It's moving at some frequency, which gives it some linear velocity, tangent velocity. Okay, and if we know the velocity, we can determine the kinetic energy. The kinetic energy is 1/2 mv squared. Okay, so let's go ahead and use that math. Right, so kinetic, and I'll just put it over here on the side. T is 1/2 mv squared, right? Which is 1/2 me, the electron mass, because it's the thing orbiting, r squared omega squared. Okay. I'm going to define a new parameter called the moment of inertia. I, right? Where I is equal to MER squared. Okay. You guys remember from physics 1, moment of inertia tells you in some sense relates the angular frequency of an object to its at fixed angular momentum to its mass and its size. So if you, again, I do rotational spectroscopy for a living, so I think about angular momentum a lot. The example I always give about moment of inertia is imagine I have, and this is the one that my PhD advisor gives to PhD students, perfectly valid, 2 figure skaters who are doing the same, who've applied the same amount of energy to some rotation at space, right? And one of them, right, so they both have the same fixed amount of angular kinetic energy, right? So they both have fixed heat, all right? And what do they call? Figure skaters, excuse me, has their arms out, and their angular frequency is slow compared to the other one who has their arms closed. So you've seen that before, and you can watch the figure skaters speed themselves up by opening and closing their arms. And all they're doing is changing R here, changing their moment of inertia, right? And so as MER squared gets larger, omega gets smaller, and vice versa. Okay, so so the moment of inertia converts mass and distance and angular frequency given energy. Okay, so in some sense, it takes more energy to spin a larger object up to some frequency than a smaller object. That should make this. All right, so we call this, like, in some sense, this is what we call the rotational mass of the system. Tells you something about how, if you think about momentum, tells you at fixed momentum how fast an object is going. It's dependent on their mass. The heavier it is, the slower it's moving at fixed momentum. Same idea here. You have some angular momentum. The bigger its mass is, the slower its velocity. Okay, so we can write now that the kinetic energy is equal to 1/2 I omega squared. And then we can define the angular momentum. The absolute value of the angular momentum is the moment of inertia times the frequency. Right? Remember, momentum is mass times velocity. So angular momentum is rotational mass times rotational velocity. Where velocity is just a rate per second, meters per second. That's a linear velocity. This is an angular velocity. It's radians per second. And you have a momentum. Momentum is m times v. Here's v, and here's m. Nothing fancy. We've just turned linear motion into angular motion. All the terms start to look funky. They have different labels, but the math works exactly the same. Right? P is equal to m times v. Just write that. Drive that point home. And so what we can write now, just kind of simplifying, is that the angular momentum of rotation is L squared over 2I. So if I want to remember now, what I want to do in quantum mechanics is I want to solve the Schrodinger equation. I want to find the wave functions that give me the energy back times the wave function. This is the kinetic energy part. So the kinetic energy operator is going to be proportional to some operator squared for angular momentum. I can put little hats here to promote these to operators. Right? And our goal will be, right, to solve T psi is equal to the rotational energies times psi, right? That's our quantum mechanical problem, right? So this is our goal, is to find the wave functions that satisfy the eigenvalue equation, the measurement for this angular momentum. We've got some steps that we have to work with. So this is all nice and dandy. I can write this, but I don't know anything about what L squared looks like. You know, I've got some math I got it, right? Because eventually I gotta come up with some algebraic equation. Right? It's gonna have some derivatives of psi over here. I think the second derivative of psi is gonna give me psi back. We always have an equation that looks like that. So I got to kind of figure out what the differential part of the calculus of this equation looks like. This is just an idea, but I don't know what L squared actually is. So I got to kind of do the math and legwork to come up with this problem. All right, well, but we can use the same idea that L squared, right? L kind of just looks like momentum. Right? It is momentum. It's just in an angular sense instead of a linear sense. Right? Things moving in a line. This is things moving on a circle. So we can take the same idea. We can say L squared over 2I is going to be equal to some normal kinetic energy. And try to go from there. Right? The math isn't so much different than we just have made things linear and turned them into angles. So the math should still apply. All right, so what we can say now, L squared over 2I, we know that this is going to look like a normal kinetic energy. Remember what the normal kinetic energy in quantum mechanics looks like? It looks like minus h bar squared over 2 times the mass, which is the electron, times the second derivative with respect to position, right? D squared dx squared. Let's get that second derivative. But here's the problem. We're now in 3 dimensions. Right? This electron can be in any position on a sphere. So we have second derivatives along all 3 directions. We have to think about its x motion, its y motion, and its z motion. Right? If you worked hard on problem set 1, you had a very similar problem where you're expanding the particle in the box from 1 dimension to 3 dimensions. You now have to think about the kinetic energy. So you have three terms now in your kinetic energy. They just sum together. Right? So it should look something like this. Well, in the end, it's just the kinetic energy is going to be proportional to two derivatives, second derivatives. That's all great. But here's the problem. X, Y, and Z is a really, really garbage set of coordinates for us to track circular motion. Right? Imagine, think about how complex it is if you're moving on some circular trajectory, how to track X, Y, and Z, right? You would need a lot of trig. You need to think about sines and cosines, think about angles. But in the end, right, we know that we can take a position X, Y, Z and just at fixed R, just give it angles. There's two angles that define this position at fixed R. So let's just do that. Let's just make the conversion and replace, get rid of X, Y, and Z altogether and convert our coordinate system into angular coordinates, polar coordinates. Okay. But I'm not going to use polar coordinates because polar coordinates are two-dimensional and we have a 3D problem. So let's just forget about polar and go to the next step, which are spherical coordinates, the coordinates of a sphere instead of a circle. So we need to convert to spherical coordinates. All right, so let's do that. Should be a little bit of review for the math nerds in the room. So let's define our coordinate system. I've got an electron sitting here at X, Y, Z. Okay. And I'm going to define three parameters to define these coordinates. First, there's the length R. There's the angle between the vector and the z-axis, theta. And then the final one is where I project this vector down into the xy plane. And I calculate the angle between the x-axis and this projection, theta, or phi. Okay, so those are our three types of coordinates. And just from back in the old days, you can show that the relationship between these is r is equal to x squared plus y squared plus z squared. Theta is equal to the inverse cosine of the z coordinate divided by r. And phi is equal to the inverse tangent of y over x. Okay. All right, so those are our three coordinates. So that gives us a formula to convert between x, y, and z to r, theta, and phi. That's really scary. I got to take some derivatives and do some conversions. So we have to do that math. That's going to be really frightening. So we'll have to get it done. We also have some differences in our domains of our variables. X, Y, and Z can take any value they want, but R, theta, and phi can only take specific values. So R can't be negative, obviously, because it's a square root. So R has to be greater than or equal to 0. I'm sorry, that's the wrong way. And less than infinity. Theta tells us where we are relative to Z. So we don't really need to go 360 degrees. We only need to go 180 degrees. Right, from Z plus to Z minus. So the theta has domain between 0 and pi. Okay. And phi, of course, this can rotate 360 degrees. Right? Point any direction in the xy plane. This one goes from 0 to 2 pi. But not including 2 pi because 2 pi is the same as 0. Those are our three variables. Now, here's what'll end up being really nice about this math. It will help us a little bit. is to think about eventually we have to do integrals, right? We have to integrate over some wave function defined in this space, right? The square, to get probabilities. So eventually we're going to have some integral of some three-dimensional function. And that integral is going to be defined in x, y, z from negative infinity to positive infinity, right? So any integral in x, y, z space is going to look like three integrals of minus infinity to positive infinity, which sucks. But if you go to spherical coordinates, two of your integrals are going to be finite, 0 to pi, 0 to 2 pi, and only one of them is going to be infinite. Okay. So, or improper, or they're called. Okay, so it does kind of help us a little bit, at least mathematically. We don't have so many infinities. The angles kind of help out with the 5. All right, so what we need to do now is to instead think about what is the kinetic energy in terms of the derivatives of the wave function in terms of these coordinates instead. Right? I need to have d squared dr and d squared d phi, and d squared d theta, and so on. So I need to start thinking about the angular momentum in terms of the angular coordinates. All right, I'm not going to do the math for this. Instead, I'm going to write out the results of it because the math is really annoying. And in my undergrad course, we were forced to. I don't have enough time to write that. Okay, what do I want to do here? Let's just stop. Let me just say one more thing, okay? And we'll finish this up on Tuesday. I think we've had a good conversation so far. All right, so our goal next, right, is to convert our kinetic energy operator, which is the thing that's going to give us our wave functions, into r, theta, and phi. Right? And what we're hoping for is that the r part is separate from the theta and the phi part, that there's no intercommunication between them. If that's the case, then that means that we can separate our kinetic energy into an angular part, a part that only depends on theta and phi, and a part that depends on r. And once we're able to do that, that's going to help us a lot. Because then we solve two problems, one on our infinite coordinate, and then one on these angular coordinates that are much easier to do. So that's going to be our goal, is to convert this into our spherical coordinates. We're going to get a horribly ugly equation. It looks terrible, but the math is much easier. And it's going to simplify out quite a bit and allow us to start thinking about what the solutions to the wave functions are to the hydrogen atom. Right? So we're going to take an L in terms of our math complexity, but we're going to take a W in terms of the simplification and the physical kind of interpretation of what's going on. It's going to make it much easier for us to visualize the solution for this. It's impossible to do it in X, Y. It just doesn't make sense. So we're going to have to do that. We're going to have to do that conversion, and then we'll make some progress going from there. All right. I'll see most of you tomorrow. Have a good one.